The design and simulation procedures for distillation are based on two important concepts. The equilibrium stage concept, introduced in 1894 by Ernest Sorel, and the concept of the Murphree stage efficiency, introduced in 1925 by E.V. Murphree. Murphree wrote in his seminal paper, "The concept of the theoretical plate does not offer a satisfactory basis of calculation for rectifying columns when the mixture being rectified contains more than two components. And even for some calculations on binary mixtures, its use is not satisfactory." Here's a schematic of the operation of a distillation tray. Let us assume that the operation is in the bubbly froth regime. YE is the composition of vapor entering the tray. Y sub L is the composition of vapor leaving the tray. And to keep matters simple, let us assume that the liquid phase in the tray is well mixed. That essentially implies that the composition of the liquid leaving the tray is the same as the composition of the liquid mixture on the tray. The Murphree efficiency for the vapor phase is defined as the actual composition change divided by the composition change at equilibrium conditions. In other words, if the vapor leaving the tray was in equilibrium with the liquid on the tray. And the equilibrium composition is Y superstar. For a binary mixture, since the mole fractions add to unity, the Murphree efficiency for component 1 equals that of component 2, and both these efficiencies must be bounded and lie between 0 and unity. For a ternary mixture, there is no fundamental requirement that the component Murphree efficiencies of each of the components in an n-component mixture be equal to one another. And indeed, the objective of this presentation to explore the consequences of unequal component Murphree efficiencies on the performance and operation of a distillation column. To gain insights into the component Murphree efficiencies, we need to adopt a more rigorous model for interphase mass transfer than afforded by the Fick's law of diffusion that is commonly used. And in this context, I refer to my presentations on uphill diffusion and diffusing uphill that are available on my YouTube channel. We proceed with our analysis by pointing out the limitations of the Fick's law of diffusion. Here is a picture taken in the Antarctica showing fortresses of ice containing nearly pure water happily coexisting with seawater containing salt. Apparently, the Fick's law of diffusion does not seem to apply here because there is no diffusion of sodium chloride into the ice fortresses. Let's examine the reasons why. This graph plots the Gibbs free energies of ice and of seawater as a function of the mole fraction of sodium chloride x1. The thermodynamic equilibrium is described by the common tangent. The common tangent intersects the y-axis at this point, in which the chemical potential of water in the ice fortress equals the chemical potential of water in seawater. At the other end, the common tangent intersects the x1 equal to 1 axis at the chemical potential of sodium chloride that is the same in ice and in seawater. We note that at thermodynamic equilibrium, the mole fraction of sodium chloride in seawater is considerably higher than the mole fraction of sodium chloride in the ice fortresses. And for that reason, there is no diffusion, despite the fact that there is a large composition difference between the sodium chloride in seawater and in ice. The inescapable conclusion to be drawn from this analysis is that the species diffusion is driven not by the composition gradient, but by the gradient in the chemical potentials of the components. Having established that chemical potential gradients are the proper driving forces for diffusion, let us see how best to set up the formulation describing the diffusion fluxes in terms of the chemical potential gradients. The most convenient formulation is to adopt the approach developed originally by James Clerk Maxwell and Joseph-Stefan to describe diffusion in mixtures of ideal gases. Let us therefore start the analysis by considering a mixture of 3 components. The force acting per mole of species 1 is the negative of the chemical potential gradient at constant temperature and pressure. This is balanced by the friction component 1 experiences in undergoing a relative motion with respect to species 2 and the friction it experiences in undergoing relative motion with respect to species 3. Similarly, we can write an expression for the force acting per mole of species 2 and relate it to the friction between 2 and 1 and between 2 and 3. We define the Maxwell-Stefan diffusivities in this manner, and the Maxwell-Stefan diffusivities are differentiated from the Fick diffusivities by using the symbol D with a line through it. On the basis of this formulation, it is evident that the physical significance of the Maxwell-Stefan diffusivities is that it represents an inverse drag coefficient. Using RT in the numerator ensures that the units of the Maxwell-Stefan diffusivities are square meters per second, as is commonly used to describe diffusion phenomena. We need the multipliers x2 and x3, which represent the mole fractions of components 2 and 3, because the friction between component 1 and 2 should depend on the relative amounts of components 1 and 2 in the mixture, and that is taken care of by these multipliers involving the mole fractions. We need consider only two of these equations because of the Gibbs-Dion constraint on the chemical potential gradients. Using two-dimensional matrix notation, we can shoehorn the set of two Maxwell-Stefan equations shown on the previous slide into a Fickian form. A column vector of molar diffusion fluxes, defined here, is related to a column vector of mole fraction gradients via a square matrix of Fickian diffusivities. Vm is the molar volume of the mixture. Using a straightforward algebra, we can derive an expression to explicitly calculate the elements D11, D12, D21, and D22 in terms of the Maxwell-Stefan diffusivities of the three binary pairs D12, D13, and D23. This expression is given here. It's noteworthy that the diagonal elements are some kind of average of the Maxwell-Stefan diffusivities, whereas the off-diagonal elements are proportional to differences in the pair Maxwell-Stefan diffusivities. As an example, let us consider a ternary mixture consisting of hydrogen, component 1, nitrogen, component 2, carbon dioxide, component 3, and calculate the diffusivities at a temperature of 308 Kelvin at the mole fraction x1 equals 0.25, x2 equals 0.5, and x3 equals 0.25. From the kinetic gas theory, the Maxwell-Stefan pair diffusivities can be calculated as 8.33 10⁻⁵ for the 1,2 pair, which is hydrogen-nitrogen. This is for the hydrogen-carbon dioxide pair, and this is for the nitrogen-carbon dioxide pair. We note that these diffusivity values are significantly higher than the diffusivity for the nitrogen CO2 pair because hydrogen is the smallest of the three guest molecules. Using this expression, we can calculate the matrix of the Fick diffusivities as follows. It's interesting to note that the cross coefficient here, D21, is minus 3.83, whereas the diagonal element here, D22, is 2.15. This implies that if we have a situation in which the gradient of the mole fraction of component 2 is 0, which is component 2 is nitrogen, then the flux of nitrogen J2 will not be 0 because it will be dictated by D21 times dx1 dz, and D21 is large and negative, and therefore we should experience uphill diffusion for conditions in which we can ensure that D2 dx2 by dz is 0. Let us see if this expectation is borne out in experiments. Using two-dimensional matrix notation, we can shoehorn the set of two Maxwell-Stefan equations shown on the previous slide into a Fickian form. A column vector of molar diffusion fluxes, defined here, is related to a column vector of mole fraction gradients via a square matrix of Fickian diffusivities. Vm is the molar volume of the mixture. Using a straightforward algebra, we can derive an expression to explicitly calculate the elements D11, D12, D21, and D22 in terms of the Maxwell-Stefan diffusivities of the three binary pairs D12, D13, and D23. This expression is given here. It's noteworthy that the diagonal elements are some kind of average of the Maxwell-Stefan diffusivities, whereas the off-diagonal elements are proportional to differences in the pair Maxwell-Stefan diffusivities. As an example, let us consider a ternary mixture consisting of hydrogen, component 1, nitrogen, component 2, carbon dioxide, component 3, and calculate the diffusivities at a temperature of 308 Kelvin at the mole fraction x1 equals 0.25, x2 equals 0.5, and x3 equals 0.25. From the kinetic gas theory, the Maxwell-Stefan pair diffusivities can be calculated as 8.33 10⁻⁵ for the 1,2 pair, which is hydrogen-nitrogen. This is for the hydrogen-carbon dioxide pair, and this is for the nitrogen-carbon dioxide pair. We note that these diffusivity values are significantly higher than the diffusivity for the nitrogen CO2 pair, because hydrogen is the smallest of the three guest molecules. Using this expression, we can calculate the matrix of the Fick diffusivities as follows. It's interesting to note that the cross coefficient here, D21, is minus 3.83, whereas the diagonal element here, D22, is 2.15. This implies that if we have a situation in which the gradient of the mole fraction of component 2 is 0, which is component 2 is nitrogen, then the flux of nitrogen J2 will not be 0, because it will be dictated by D21 times dx1 dz, and D21 is large and negative, and therefore we should experience uphill diffusion for conditions in which we can ensure that dx2 by dz is 0. Let us see if this expectation is borne out in experiments. Duncan and Torr in 1962 published a set of experiments in a two-bulb diffusion apparatus with the ternary mixture of hydrogen, nitrogen, and carbon dioxide. The initial compositions of this mixture in bulb A is shown by this point here, and the initial composition in bulb B is shown by this point here in the ternary composition space. At time t equal to 0, the capillary tube connecting the two bulbs is opened, and the interdiffusion is allowed to take place. The composition trajectories followed in bulb A is indicated by the red circles, and in bulb B by the green squares. It's interesting to note that the equilibration trajectory does not follow a straight line path, rather it has a serpentine character. In this graph, the set of data on the mole fractions in bulb A and bulb B are plotted as a function of time. The equilibration of hydrogen and carbon dioxide follows the exponential trajectories one would normally expect for a diffusion governed equilibration process. Nitrogen, on the other hand, has a different character. The initial composition of nitrogen in both bulbs is exactly the same. In other words, there is no driving force for nitrogen, and yet this does not prevent nitrogen from diffusing. For example, in bulb A, the composition decreases from the initial value of 0.5 and continues to decrease till this point is reached, and then it increases in value. The composition in bulb B, on the other hand, increases from 0.5, reaches a maximum, and then decreases eventually to equilibrate at very long times. During the interval 0 to 6 hours, nitrogen experiences uphill diffusion. As was expected on the basis of the calculations we presented in the foregoing slide for the Fick diffusivity matrix that was evaluated at the average between this composition and this composition. So the uphill diffusion is a direct consequence of the friction between components 2 and 3. Even though the composition gradient of nitrogen is 0, due to the large drag between nitrogen and carbon dioxide, nitrogen is dragged from bulb A to bulb B. From bulb A to bulb B, as a consequence, the mole fraction of nitrogen decreases in bulb A, and concomitantly the mole fraction of nitrogen in bulb B increases. Therefore, we draw the conclusion that even in a ternary gas mixture, it is possible to experience uphill diffusion due to differences in the drags coefficients of the 3 binary pairs. Another conclusion to be drawn, as will be confirmed in several examples to be presented later in this presentation, is that a consequence of uphill diffusion is that the equilibration trajectory that is followed in composition space has a serpentine character. We ask ourselves the question whether the interdiffusion of the ternary gas mixture in the 2 bulb diffusion experiments of Duncan and Tour violates the second law of thermodynamics because of the uphill transport of nitrogen. The second law of thermodynamics mandates that the rate of entropy production be positive definite. The entropy production for the ternary mixture is given by this expression, where J1, J2, and J3 are the diffusion fluxes of hydrogen, nitrogen, and carbon dioxide. And these represent the gradients of ln x1, ln x2, and ln x3, where x1, x2, and x3 are the mole fractions. For uphill diffusion of nitrogen, this term, this contribution of this term is negative. In other words, nitrogen consumes entropy. This is not disallowed because hydrogen and CO2 produce entropy at such a rate that the overall rate of entropy production is positive definite. The Maxwell-Stefan approach for diffusion in ideal gas mixtures can be extended to non-ideal systems by introducing thermodynamic correction factors that involve the activity coefficients. The thermodynamic factors can be calculated for liquid mixtures using, say, the Nonideal and Uniquac equation, for supercritical gases using the Peng-Robinson equation of state, for polymer solutions using the Fleury-Huggins model, for metal alloys using the Calfad model. For a ternary mixture, the departures from ideality is described by a matrix of thermodynamics correction factors whose off-diagonal elements are generally large and non-zero. The off-diagonal elements of the thermodynamic factor matrix contributes to a large extent to the off-diagonal elements of the Fick diffusivity matrix, and these off-diagonal elements lead to the phenomena of uphill diffusion, as we shall see in the next slide. Let's gain some understanding on the behavior of diffusivities in the non-ideal ternary mixture of glycerol, acetone, and water. This system has a region in which we have phase separation. The green line represents the binodal curve, and the red line denotes the spinodal curve. Along the spinodal curve, the determinant of the matrix of thermodynamic correction factors is 0, and consequently, the determinant of the Fick diffusivity matrix is also 0. Let's look at the elements of the matrix of Fick diffusivities as we move along this line from composition A to composition B to composition C to composition D. For composition A, the elements of the matrix of Fick diffusivities has these elements, and if we take the product of the cross coefficients and divide by the product of the diagonal elements, the ratio is found to be 0.01725. This ratio increases as we approach the region of phase immiscibility. And consequently, the magnitude of the coupling effects increases as we approach compositions close to phase separation. This has severe consequences for composition trajectories in regions close to the two-phase region. The entire set of experimental data of Grossman for the elements of the Fick diffusivity matrix in the homogeneous phase regions of the ternary mixture glycerol, acetone, water are replotted in this diagram. The y-axis represents the relative coupling effects of the D matrix, this is expressed as the product of the cross coefficients divided by the product of the diagonal elements. The x-axis represents the relative coupling effects in the thermodynamic correction factor matrix that is calculated using the Nonideal model, and the relative coupling effects are described by the product of the off-diagonal elements divided by the product of the diagonal elements. We note that there is a good correlation between the relative coupling of the Fick diffusivity matrix with the relative coupling effects due to thermodynamic correction factors. We conclude that thermodynamic coupling is the major contributor to diffusional coupling in organic liquid mixtures. Also notable is the fact that these coupling effects increase and are maximum at the spinodal composition, which is plotted by the stars here. This expression for the elements of the matrix of Fick diffusivities as a product of two matrices can be used to estimate the elements of the Fick diffusivity from information on diffusivities in the corresponding binary mixtures of the pairs glycerol water, glycerol acetone, and acetone water. For example, experimental data on the Fick diffusivities for the system acetone water are shown by the red circles. By dividing the Fick diffusivities by the correction factor gamma, we obtain the Maxwell-Stefan diffusivities, and the Maxwell-Stefan diffusivities indicated by the green squares shows a predictable composition dependence, and these can be estimated, say, using a interpolation formula on the basis of the self-diffusivities at either end of the composition range. So similarly, D13 can be estimated from experimental data on diffusivities in the binary mixture 1 and 3 and from the binary mixture of 2 and 3. So this matrix can be estimated from the constituent binary pairs. The matrix of thermodynamic correction factors can be estimated from say the uniquac or Nonideal parameters for phase equilibrium, and this affords a straightforward procedure for estimation of the Fick diffusivities. Consider the experimental data reported in 1985 for interdiffusion in the system glycerol, water, and acetone. These experiments were conducted in a Lewis stirred cell. The bottom cell contains a mixture of glycerol and water at this composition. The top cell contains a mixture of acetone and water at this composition. And at time t equals 0, the stirrers are rotated and interdiffusion is allowed to take place. The experimental data showing the approach to equilibrium is shown by the open circles in either phase. If we join this point with the initial point here, the mixture composition ends up in the two-phase region and the phases will equilibrate to the compositions shown at the end of this tie line. So in the glycerol-rich phase, the equilibration trajectory is from x0 to xeq, and in the acetone-rich phase, the equilibration is along this line. Note that the trajectories are not linear, but curvilinear or serpentine. The blue lines show the model calculations using data on the Maxwell-Stefan diffusivities and thermodynamic correction factors calculated from the NRTL parameters and information on the diffusivities of the corresponding binary pairs: acetone water, water glycerol, and acetone glycerol. So the serpentine trajectories can be predicted from the data on thermodynamic non-idealities, along with data on the diffusivities of the corresponding binary pairs. The message to be drawn here is that serpentine trajectories are the result of diffusional coupling effects that are engendered largely by thermodynamic coupling effects. The experimental data shown on the previous slide on equilibration in the glycerol acetone water system were obtained at the University of Manchester in the department in which Professor George Leonard Standart was the department head and also the supervisor in charge of the experimental work on ternary extraction, ternary distillation, which I will discuss in the subsequent slides. Important point to note is that George Leonard Standart died in 1978 at the age of 57. And he started his studies in chemical engineering at Caltech in the United States in the early 1940s. Indeed, this picture is taken from the yearbook of Caltech. And Professor Standart wrote several papers on the theory of irreversible thermodynamics that were published in chemical engineering science in the late 60s and early 70s. So this is by way of tribute to the contributions of George Standart to the development of a rigorous theory of mass transfer and applications to distillation, extraction, condensation, and absorption. Indeed, Standart was the driving force behind the experimental work at the University of Manchester that attempted to demonstrate the limitations of Fick's law and also to show that Murphree efficiencies in multi-component distillation can assume negative values. This is the topic I will take up in the next slide. Having examined the Importance of diffusional coupling effects in mixtures of ternary gases and ternary non-ideal liquid mixtures. Let us turn our attention to ternary distillation, and we start by examining distillation of a mixture of water, ethanol, and acetone. Acetone is the most volatile component with a boiling point of 329.7 Kelvin. Water is the least volatile component with a boiling point of 373.15 Kelvin. Ethanol is a component with intermediate volatility and has a boiling point of 351.6 Kelvin. The ethanol water mixture has an azeotrope of composition approximately 90% ethanol, 10% water, and the azeotrope boils at 351.4 Kelvin, slightly below the boiling point of ethanol. For a distillation column operating under total reflux conditions in which the stages are in equilibrium, we can construct residue curve maps shown by these pink lines. They describe the trajectory the compositions in the distillation column will follow from stage to stage. We note that any feed mixture composition in this part of the diagram below the thick black line, which is called a distillation boundary, any feed mixture here cannot end up in this part of the composition region, because the residue curve maps do not cross the distillation boundary. Therefore, in a normal distillation column, it is not possible to break the azeotrope if you're in this region of the distillation column with your feed mixture. We ask the question whether the distillation boundaries can be crossed because of coupled diffusion effects that were described for ternary gas mixtures and ternary liquid mixtures. This question was posed in the dissertation thesis of Martin Springer. This is the experimental setup used by Martin Springer. All the experiments were conducted at total reflux conditions in a column that consists of a glass column that consists of bubble caps, and the vapor compositions at the various locations shown here, and the liquid compositions were monitored. Samples were taken and the compositions determined This is a photograph of the distillation apparatus. Details will be found in several publications with Springer as the lead author. The experimental data in one of the experiments of Springer are shown by the blue circles. This is a reboiler composition, and in this is the condenser composition, and we note that the experimental data show that the distillation boundary has been crossed from the bottom half to the top half as we move up the column from the reboiler to the condenser. This boundary crossing needs further examination and elucidation. In order to rationalize the boundary crossing phenomena observed in the Springer experiments, let us construct a simple model of the distillation operations. In the glass column used by Springer in the experiments, we are able to observe the bubble dispersions on the tray. We can have an estimation of the bubble size, and in the model we take the bubbles to be of uniform size, 4.5 millimeter in diameter. The bubble rise velocity can be estimated from experimental data, and a value of 20 centimeter per second is a good representation of the bubble rise velocity for a 4.5 millimeter sized bubble. The average froth height can be measured, and we take 9.2 millimeter froth height as a reasonably good estimation of the dispersion height on the tray. The contact time of vapor and liquid can be estimated from the rise velocity and the froth height, and we determine the contact time to be 46 milliseconds. The diffusivities in the vapor can be estimated from the Fuller-Shetler-Giddings equation, and the values for the system water, ethanol, acetone, components 1, 2, and 3, the values are D12 is 1.98, D13 is 1.72, and D23 is 0.856. All of these 10 to the minus 5 square meters per second. We note that the ethanol water diffusivity, the 2,3 diffusivity, is about a factor 2 lower than the D12 and D13 diffusivities, because water is the smallest molecule and ethanol and acetone are significantly larger than water. In other words, we note here that the drag between 1 and 2 and 1 and 3 and 2 and 3 are not the same, because these diffusivities are a representation of the inverse drag, as was explained in our analysis of the Duncan Tour experiments. For a given set of conditions close to the distillation boundary, we can estimate the matrix of Fick diffusivities, and we note in this case the cross coefficient D21 is large, relatively large and negative. So the vapor phase has a strong element of diffusional coupling. For a spherical bubble that rises in a liquid, the equilibration process is described by the Geddes model. This is a classic model. And we can use this model to calculate the composition trajectories that are realized as the vapor emerges from the bottom, crosses the froth, and leaves the distillation tray. We also determined that the liquid phase resistance is relatively unimportant, and therefore the interface mass transfer is largely dictated by the vapor phase transport. Let us perform the calculations using the Geddes model described in the previous slide. We take the composition of the vapor entering the tray just below the distillation boundary at this position, and this is a blow up of the composition diagram. So this is the composition of the vapor entering the tray. Using the Maxwell-Stefan equations and the Geddes equation for diffusion in the vapor phase, we can calculate the composition trajectory the vapor follows as it equilibrates in passing through the tray. And the equilibration trajectory is shown by the blue line. If the tray was the dispersion height in the tray is sufficiently high such that equilibrium is reached, then the equilibrium composition would be reached, indicated by the point here. And if we connect y0 to the y equilibrium composition, we obtain the pink line as described by the residue curve map. And the residue curve maps, not surprisingly, show no boundary crossing is possible. However, the serpentine trajectory followed during the equilibration process stops at a time of 46 milliseconds because the froth height is not large enough for equilibration to occur. And the consequence is that the composition leaving the tray has crossed the boundary. So again, we have the same observation as in the Duncan-Tour experiments, that the serpentine equilibration trajectory is followed due to diffusional coupling effects. Indeed, we can calculate or back calculate from the basis of the composition trajectory the component Murphree efficiencies, and we note that the Murphree efficiency for water is significantly higher than that of ethanol and that of acetone. And therefore, it is the differences in the component Murphree efficiencies that lead to boundary crossing. If all the component efficiencies were equal to one another, no boundary crossing effects would be detectable. The takeaways from this presentation are summarized in the slide. Transient overshoots and serpentine equilibration trajectories in composition space are signatures of uphill diffusion. Put another way, uphill diffusion follows the scenic route For ternary distillation, uphill diffusion can cause distillation boundaries to be crossed. And we could ask the question, can such boundary crossing effects be exploited for practical gain? We will address this question in a future presentation.